which means we have now time to practice. So today we're going to practice on board work. We're going to make some MO diagrams. Okay, so we're just going to start from scratch. I want to say, give me the MO diagram for bromine molecule, and so we'll work on that. But let's look at the schedule. I moved the Jablonski diagram up to Wednesday, and then electronic spectroscopy selection rules on Friday. And then on Monday of the Thanksgiving week, we're going to look at the iodine lab analysis. So I'm going to take your questions on the iodine lab analysis. You will have already spent a week working on it. So you're doing that this week, and so next Monday in class, I will show you some things on the computer that will help with that analysis and answer some questions. And then that lab that week, it says Lab 10 Rough Draft Revisions. That's just a time where you can come on Monday or Tuesday and ask your questions. We won't be here Wednesday or Thursday, obviously, but you can come on Monday or Tuesday if you have questions on the formatting or anything like that. Either Crescencio on Monday or Nick on Tuesday can answer your questions and just make sure that you have a really good report for this last big final report. Okay? But the Q&A on Monday, I'm going to definitely address the propagation of uncertainty on that too. So if you're a little bit confused on that, that's the time when we can really talk about it. Because we will want to get the propagation of uncertainty, the uncertainty on those anharmonicity constants, because they're multiplied by the vibrational frequency. So you've got to figure out how to take the vibrational frequency out and its uncertainty out to see what the uncertainty is for the anharmonicity constant. It's very easy, but if you haven't done it before, you should have done it for the CO lab, but if you were fuzzy on that, we will get another bite of the apple. Now, today's MO diagram practice on the board. So we're going to do bromine and we're going to do ammonia. So we're going to do a diatomic and we're going to do a non-diatomic. We're going to do a more complicated molecule. And so bromine would be something that I would feel justified in asking you on an exam. Ammonia would not be like the full diagram, something I would ask you on an exam, but I might, if I showed you say I showed you an ammonia MO diagram, you should be able to look at it and understand it, like what atomic orbitals went into this molecular orbital and things of that sort. We've practiced on that even on a Kahoot. Here's a molecular orbital for water, what atomic orbitals went into it. And so I've been kind of beating that drum, wanting you to analyze molecular orbitals and think in terms of atomic orbitals. So we're going to practice on that stuff today. Before we get started, any questions? Okay, so there's plenty of space up front, and this is going to be tiny because we don't have very tall boards, and so if you want to scoot forward, do that now, because you're not going to be able to see the fine detail that you're going to need to see. Now, I don't like to teach to the test, right? This idea of telling you, oh, molecular orbital or diatomic would be something that I might ask you. That's something that anybody who wants to test if you've been through physical chemistry before would be able to ask you. So if you're taking the chemistry version of the GRE, guess what? You're probably going to have some questions about a homonuclear diatomic MO diagram. Now, most of those are multiple choice tests, so it's not like you can draw one for them, but they may ask you questions about one, and you may have to draw it so that you can answer those questions. But it's something that every physical chemist ought to be able to do when they get through an undergraduate course in physical chemistry. So what is the molecular orbital diagram for PR2? So this is going to be our assignment, and then we're going to want to know things like bond order, label the HOMO and LUMO. What other kinds of things could I ask?
The bond length, paramagnetic.
Yeah, paramagnetic, very good, paramagnetic. The bond length might be in comparison to others. We wouldn't be able to get the bond length, but we might be able to ask, is it going to be longer or shorter than, say, diselenium, right, which would be the one just next to it. We could compare it to also fluorine and chlorine, and bromine's just bigger atoms, so naturally that's going to be a longer bond length for bromine than for chlorine or for fluorine. So let's begin with the MO diagram. We put the molecule in the middle. And let's go ahead and draw the coordinate system on here. This is the z-axis. And so if that's the z-axis of the molecule, what are the other two axes? What's the one going up? X, very good. X and Y. Okay, so this counterclockwise right-hand rule, that would be our coordinate system. And so if I were to draw a p orbital that's going like an infinity sign, that's going to be the p what orbital? PZ, because it's going left and right, and that's the z-axis. Okay, so this is going to be the middle part. This is where the molecule, all the molecular orbitals will be here. And so what goes on either side are the atoms and the atomic orbitals. So this is just a bromine atom on the left, bromine atom on the right. So let's draw the atomic orbitals for bromine. Don't draw them up here because you've got to have antibonding, so then you need to draw them something like this. So we have space for the s orbitals to bond and antibond, and the p orbitals to bond and antibond. This is the artwork part of physical chemistry. These are homonuclear diatomics. So the energy levels should be the same. They should be about the same horizontally across from each other. If we were making HBr, okay, let's just pretend, if this was an H, what orbital do we have for hydrogen? We only have the 1s. Where would that 1s be? Would it be down here? Would it be up here? It'd be closer to the top orbital on the bromine. Those last orbitals are going to be about the same energy, so it'd be closer down here. Okay, just to let you know, all the sort of the highest orbitals in any sort of valence system. So the 1s orbital is the valence orbital for hydrogen, and the p orbitals are the highest orbitals for the bromine, and so those are going to be pretty close to each other. Okay. Just so you know, those valence orbitals of the atoms are going to be across from each other. So let's populate our bromines. Now, what are these orbitals? Which s is this?
4.
Yay, so you start with bromine and you come straight across the periodic table and you see the period 4. So it's the 4s, and that's the 4p. Just for grins, what's scandium? What is he? This is, yeah, scandium, titanium, that's what group?
It's 3D.
3D, okay, so even though that's on row 4, it jumps down a principal quantum number, that's the 3D block. Let's fill this quickly with our valence electrons. How many valence electrons does bromine have?
4.
Valence electrons.
Oh, sorry.
1, 2, 3, 4, 5. Look how I'm filling it. If I had 5, that's where I'd stop. 6, 7. Same on both sides. 1, 2, 3, 4, 5, 6, 7. So these are our atoms. These are the ground state electron configurations for both atoms. Now they can come together and mix in phase or out of phase. So if the s orbitals mix in phase, then you have this bonding arrangement. That would be a sigma bond. That's going to be lower in energy. Now think about it. If you've got electrons in 2 electrons in a 4s orbital on bromine, the size of that orbital is about this big. But now, without any nodes, that same orbital encompasses something much larger. What do you have? You have a drop in energy, don't you? You have a bigger box. So the particle in a box, if I've got a bigger box, I've got a lower energy. And so this bonding orbital drops down to here. Now if they're out of phase, you've got more curvature. And curvature is energy. So you've got more curvature, you have a node in the middle, and so then you have a higher energy. So it's going to be here. And because we're dealing with homonuclear diatomics, it's very easy to identify those as a sigma and a sigma star bond. So if we draw the molecule here, let's draw the MOs. Let's put that on our list. Draw the MOs. And what I'm going to do for drawing these MOs, I'm not going to try to make them beautiful. I'm just going to show the atomic orbitals and the shading on the atomic orbitals. So you can see down here both atomic orbitals are shaded. That means there's no node. And it goes over the whole molecule. So that's the bonding molecular orbital. Here, the 4s orbitals are out of phase, and so there is a node. And so then this has got higher curvature, higher energy. And then we draw these diagonal lines just to show that primarily these two orbitals came from the two 4s's. And that just kind of helps us keep track of where this molecular orbital came from. So that's the first sigma and the sigma star orbital. Now we get to mix the p orbitals. It's a little more complicated. Let's go ahead and draw the three of our p orbitals on here. So let's start with the pz here. And so that's going to be an orbital like that. So these are our pz orbitals. They're going left and right along the z-axis. And if they come together to touch, then they can overlap. And if they're in phase, they'll bond. If they're out of phase, there'll be a node between them. And so then let's bond them in phase. Let's essentially swap the color on that one so that they can overlap and be in phase with each other. So down here, we'll have a sigma. And I'm going to draw the two atomic orbitals. So like I said, I've just shown the straight up atomic orbitals and shaded them the way they would interact in a bonding situation. So you see there's no node in the middle, so that's bonding, that's a sigma bond. That's the pz orbitals coming together. What if they were out of phase? Then we'd have the sigma star. So let's go way up. That's going to be our highest energy interaction. This one has two nodes, here and here, on the atoms. This one has three nodes. You see the different colors, the different changes in shading. So it has higher curvature, so it's higher in energy. Does everybody understand what I'm talking about with curvature? You know, the wave function's curving more. If it's swapping sign, and remember these are sign of the wave function. So positive sign, negative sign, positive sign, negative sign. If it's swapping sign a bunch, that's curvature. And curvature is energy from the Schrodinger equation. The Hamiltonian is the second derivative operator operating on the wave function, and that second derivative is curvature. So if a wave function has lots of nodes, it has lots of energy.
Okay, so for the sigma star up there at the top, when you said there are three nodes, the three nodes are in between the different shadings?
Yes, let me draw with the different color. So here's a node here, here, and here, there, and there. And you can see in energy it progresses from 0 nodes, 1, 2, 3. So it just gets higher in energy as you go up. The more curvature you have, the more nodes you have. Now we get to mix the p orbitals that are side-on interactions, the px and the py. It's a little bit more difficult to draw, but let's start with the px because that's still in the plane of the board. So that's the one that goes up and down. And so if these come together on the side, then they can bond if they're in phase with each other, and they can have an antibonding if they're out of phase. Now, whether they bond up like this or out like that, it's the same overlap, it's the same curvature, it's the same interaction, so it's going to be the same energy. So the px and the py are really the same, they're just rotated 90 degrees. So it's going to be the same interaction, but different orientation in space. So this is going to be two energy levels that are degenerate. And so if we drew this picture, so I just drew the px orbitals with the shading on the same side, and that's the pi bond. So that's our pi bonding orbital. Notice I could have drawn one of the shadings the other way, and that would be the antibonding. So above that is this picture. Doesn't matter which one you flip, but now they're out of phase. So if we have the nodes on that one, notice all of the pi bonds have this planar node that contains the bond. But this one has a node in the middle that breaks the bond. So this one has a node, but that node does not break the bond. So it's still a bonding orbital. This one has a node that does break the bond. It's between the two atoms. In fact, it's also a planar node, if you want to think of it. So that's going to be pi star. Now the others, the PYs, are going to be the same two pictures, but rotated 90 degrees. So they'll be coming in and out of the board. They're a little more difficult to draw, but I'll draw them anyway, so we can do that. How do we draw a PY orbital? Well, look at the y-axis. So it's going to be diagonal. It's going to be a node that comes out here, and then the other one's going to be kind of behind it. This one's maybe a little better than that one over there. So you see the shaded parts outside of the board and the unshaded parts back inside the board. And it's diagonal a little bit to correspond to the y-axis. So I've drawn the two shaded ones coming out of the board and the two non-shaded ones going into the board, kind of diagonal. You can kind of see that. And then I'll draw the same thing up here. Now they've swapped shading. This one's shaded in front, that one's shaded in back.
And they can share the same orbital as PX? Or no?
So they're the same energy because they're the same size. They have the same number of nodes. Everything's the same about them except their orientation in space. The PX goes up and down, the PY goes front and back, but everything else about them is the same, so they're the same energy.
Okay.
Yeah. They have, this one has the nodal plane, the plane of the board. This one has a nodal plane that's the plane of the board, but also this plane that breaks the bond. And so this one has that node that breaks the bond, so it's a pi star. And so it's already labeled pi star over here, implying both of those are pi star. And so now we can take our 14 electrons. We've drawn all the molecular orbitals, and you could put electrons up here, but what's going to happen when this molecule goes down to the ground state? They're all going to go to the bottom. They're going to go as low as they can go. So we have 14 total electrons. We need to just start from the bottom and add them up. So 1, 2, 3, 4, 5, 6, 7, 8. Look how I'm doing it. Unpaired first. 7, 8, 9, 10, 11, 12, unpaired first. If we were done, this would be paramagnetic, but we're not done. 13, 14. So that's our molecular orbital diagram. It's populated now with electrons from the lowest orbital all the way to the top, 2 electrons per orbital. So that's Hund's rule, okay? Unpaired first, and then you can only put 2 electrons. Pauli exclusion principle says only 2 electrons, because no 2 electrons can have the same number of same exact set of quantum numbers. And so you have spin up, and then you have spin down, and the next one would be spin up or spin down, and it would match one that's already there, and it would have the same set of quantum numbers. It's really, every electron has its own address in a particular molecule, and those quantum numbers are everything about that electron.
I was just like, there's no one up there, but it's not excited to the sigma.
Right, so there's an empty antibonding orbital up there. And so then we get to our homo-lumo labeling, if we wanted to label that. This is where a separate color helps. So both of these actually is the highest occupied molecular orbital. Think about the acronym, highest occupied molecular orbital. Molecular orbitals are in the middle. That's the highest occupied one. It should be so simple to label those. You'd be surprised when people miss it. I'm surprised when people miss it. So this is the LUMO. What does LU stand for? Lowest unoccupied molecular orbital. So this is the lowest energy unoccupied molecular orbital. Let's calculate the bond order. So number of bonding electrons minus the number of antibonding electrons divided by 2. So we add up the bonding. So we have 2, 4, 6, 8. 8, 2, antibonding here, 4, 6. 8 minus 6 over 2. So bond order equals 1. And that's nice. It matches our Lewis dot structure, which is our local bond version of the molecule, where we would put a single bond between the bromines. Okay. Is it paramagnetic or diamagnetic? Diamagnetic because everything's paired up. We don't have any unpaired electrons. So this molecule is not magnetic. You put it in a magnetic field and it doesn't have any magnetism. So now for a little bit that we built this so systematically and we knew what orbitals came in. If I throw this picture at you, everybody look at this picture here, and I say, what atomic orbitals on bromine fit this, were contributing to this molecular orbital? So what atomic orbitals on bromine contribute to this molecular orbital? It's p orbitals, right? At least you can eliminate the s's, right? Right? You look at that and you're like, okay, there's not any of those answers that have s in it. Okay, there might be a 2p, a 3p, a 4p, so don't forget the principal quantum number. So you can throw out the 2p's, you can throw out 3p's, because this is bromine. You look at the periodic table. As soon as you see 2, 3, or 4, you're like, oh, I got to pay attention. What row is it on? Okay, so you get the 4p. But then you got the XYZ issue. And you're looking at it, and the way it's drawn here, X is up and down, and those p orbitals are up and down. So those are px orbitals. So they would be the 4px orbitals that contribute to this molecular orbital. So that's a legitimate question. A very simple question I can ask, and you should be able to do it very quickly. That should take you 10 seconds. You know. If you see the 2, 3, and 4, maybe another 2 seconds to look at the periodic table. Right? Yes?
So you're going to give us, for example, if you do give us the question like that, you will give us the diagram and then the grid?
Yeah, so there might be, you know, just if you wouldn't have to have the whole diagram for that. If you just have bromine and you see that it's a pi bond, okay, it's either the px or the py. Okay, now if I have only an x option, then that's your answer. If I have an X or a Y, then you can't really tell me, right? If I said the 4px and the 4py were two options on that one, you really couldn't tell me, because I could have drawn this coordinate system to where this is a totally legitimate coordinate system. Sorry, I'm running around here. Z, X, Y, and so then that orbital would be combining the two PYs, okay? So you have to know the coordinate system. I do know it's not the two PZs. 4PZs, thank you. I do know it's not the 4PZs because the Zs are end-on interactions in all diatomics. If it's a diatomic molecule, the Z-axis is the axis of symmetry. It's that C infinity axis. It's the one that contains both atoms. But the X and Y are interchangeable. I can rotate the X into the Y and the Y into the X. So that's why also they're the same energy. It really doesn't matter which one you have. Yes?
I just want to clear this up in my head so I don't get stuck on if something encounters something like this on here. So in that situation where you give us this picture but don't give us a coordinate system, and you say 4px, 4py, 12pz, and then not enough information in that particular situation.
Yeah, that would be a really hard question, but you would have to choose not enough information if you had 4px and 4py and no coordinate system. You don't have enough information. But I know that maybe one or two people would get that, and that's not my goal. Right? So I would make it a little easier than that and say only give you the X or only give you the Y. Yeah. Yeah. With the coordinate system there, so that you can make sure. Okay? But yeah, that would be the hardest way to write this question, is to just not give you enough information, but make you think you had it, Right.
It's really
Yeah, that's people say, I always worry about multiple choice being easy, right? But it's not necessarily easy. You got to know, you got to be able to transfer information like we've shown. Yes, Venus?
So for the pi bond and orbital right there.
This one? Yes.
The one on your left. Yes. So when you have that drawn there, is that in line with the bond, that the pink square?
The pink square is the board, is the plane of the board, and these p orbitals are coming out and into the board, and they're bonding side on. And this line right here is the bond between the two bromine atoms. So each of these orbitals is centered on a bromine atom. So they're close enough that those p orbitals bump into each other. And when they're in phase, it's like two water drops get close enough and then they wet. Okay, so that's the way you need to think about. So we talked about imagination. Imagining these orbitals. These orbitals are not hard. Okay? They're more like candle flames than anything else. And if you get two wicks of candles close enough together, the flames join. Okay, so thinking of these electron orbitals as more flexible like candle flames, that's a better picture. Now, there's not a positive and negative deflection of a candle flame, so I can't really show, like, it'd be cool. We need a candle with a dark and light side, like looking into the darkness and the light. But, if they got close together, the dark and the light would like suck into each other and join together if they were in phase. And if they were out of phase, they would avoid each other.
So essentially what you're saying is that with the candle analogy, both of them would cancel each other and just make one uniform plane.
Yes, and so this has a uniform shaded region out front and a uniform unshaded region out back. And remember the shaded parts, these are waves. So this is positive and negative deflection. So the whole cloud is getting bigger out front and shrinking back there. And then sometime later it's getting big back there and shrinking in front. So the electron cloud is oscillating this way. Okay, and then this one here on this side is oscillating up and down. And so that's why it has X character. And it can interact with X polarized light. And so we would know also the Millikan notation for these. If we had the D infinity H character table, I should have asked you that. What's the point group for this? D infinity H, good job. Okay, so we have the D infinity H character table, and this orbital has X symmetry. And so you can go find X in that row, find what row X is on, and get the symmetry of that. It's going to be E something. Now, how do I know it's going to be E and not A or B or whatever?
It's
Doubly degenerate, right? You have two orbitals here. Whenever you have two degenerate things, that's an E. If I had three orbitals that were degenerate, that'd be a T. So in the tetrahedral group, some of the octahedral rows, those have T's because there's three degenerate orbitals. But if it has two degenerate orbitals, it's an E in the character table. So you can eliminate all the A's and B's, and you know it's going to be one of the E's. You find X in there, and it's going to be E. Now, is it going to be G or U? If you look at this orbital, does it have inversion? Is it a +1 inversion or a -1 inversion? These are great questions. So if I invert this wave function, and you should know what that means, if every data point goes through the origin to the other side of the molecule, does the shading change? And in this case, it does. Let's pick a point. Let's pick a point right here. That's all you got to do is pick a point right here and walk through the center of mass, which is right there, to the other side of the molecule. Is it a different shading? Yes. So it's U. It's Ungerada. It's a -1 under inversion. So this would be EU. It's a great review, isn't it? And both of these are EU, so this is EU as well.
So the one on top would be EG.
Yeah, let's do this one next, okay? So if I pick that same spot and I walk through the center mass, it's the same shading. So that's G. And it's doubly degenerate, so that's E. So it's EG for that one. That's great, okay? And so then, if for some reason we had some empty space up here, and I wanted to know if I could get light to take an electron from this orbital to that orbital, I could set up my transition dipole moment integral. So let's do that. Let's pretend. Can we go from an EU to an EG? Probably best just to work right here, okay? So that's my question. Is that integral going to be equal to 0 or not equal to 0? So would this be an allowed transition if we had space for the electron? Naturally. What goes in the middle? If we're dealing with direct absorption, which is sort of what I'm setting up here, direct absorption of light is going to be the X, Y, or Z polarized light. And we've already determined that X, this has got X symmetry, this has Y symmetry, so XY light is EU. So for XY, X comma Y, polarized light, that's EU. Now let's just focus on the G's and U's for a second. We know it will be allowed, meaning it will be non-zero, if we have top row. And the top row in any character that has G's and U's is going to be AG or A1G, but it's going to be G. And so U times U is G, and then G times G is G. So we have U times U is G, and then that result G times G is G. So it's at least possible that this could be allowed. Sometimes it's impossible. If you have only one U, that wrecks it. Because 1u times any number of g's is still going to be it's still going to be uneven. It's still going to be ungerada, right? So if I have an odd number of u's, then that integral equals 0. I can tell really quickly when it's going to be 0. Sometimes to see if it's going to be non-zero, I have to do the whole thing. So it's at least possible this will be non-zero. We have to do the whole thing to be sure. So let's look at this. E times E. So we go to the character table, the direct product tables. And the little subset that I gave you, I don't think we have the d infinity h. Yeah, that's unfortunate.
You can think times itself is always the top row, right?
Just one second. And the d infinity h, now that I look at it, has some 1s and 2s associated with it. So this we can add in our diagram. It's E1u, so it's E1u. We wanted to be a little more precise. So can we go ahead and add those numbers? It's E1u for this x and y. And this is E1g.
And just a quick question. So for those high star orbitals,
Yes.
just the Cartesian for that is x, y, or y, z.
Yeah, so if we look at this pattern, thank you, this is a good time to look at that. Let's look at this orbital. If I wanted to know the Cartesian symmetry for this one, you know, what I did to get the E was I said it's doubly degenerate, so it's E. And it's Gerada through inversion, so it's G. But how do I decide between 1 and 2 on this character table? I've got to figure out the Cartesian symmetry for this one. So if I'm looking at this, what let's look at these two planes here. That kind of gives me this x spot. The center of mass of the molecule is always the origin, and so compare it to this, right? We've got the px orbital. They're on the z-axis, and so it's these 4 quadrants that go plus, minus, plus, minus. Do you remember that pattern? It's 2 axes times each other. You just have to figure out which 2 axes. So which 2 axes are we dealing with? We're dealing with the x-axis and the z-axis. The y-axis is coming out of the board, and that's not participating in this pattern of plus, minus, plus, minus. It's the x-axis and the z-axis. So this right here, this pattern is x times z. X times z. And so then that helps me decide between E1 and E2. You look on here, the xz is E1g. You say, golly, do I need to know that? Yes. That is something you can figure out. Again, it's just looking at these orbitals and considering the symmetry. What I really want you to do is train your eye to see that pattern, plus, minus, plus, minus. That's when I beat the drum on pretty good. And so that tells you it's E1g, it's the xz row. And over here, we're dealing with the y-axis and the z-axis, and so that's going to be the yz symmetry, same row. Let's see that on the character table. Okay, so now we're up here, and we're going to have to figure out the direct product of these without the direct product table. This can be done. I would not do this to you, but it can be done. Okay. Look at the octahedral character table. That's probably the most symmetric table we have. You know, the octahedral has the most symmetry elements of all of the ones that we have. And we have E times E in that table. Okay. And in fact, that or the D6H. the D6H has E1s and E2s. So let's use that one actually. So go down to the D6H direct product table, and we see E1 times E1. E1 times E1 is going to be, it's going to be A1 plus A2 plus E2. Yeah, that'll work. And so then we add the G's on there. And so since U times U is G, we have G's on here. And now I take this E1G here and multiply it by each one of those pieces in the set. So the set expands. Notice also, it's kind of interesting, this is something that's of order 2, doubly degenerate, times something that's of order 2, times it's doubly degenerate, and we get 4 things out. We get a singly degenerate, and a doubly degenerate. So we have 4 things. So the set expands. If you got 2 things times 2 things, you end up with 4. You know, and so then we're going to do this again. We're going to take this times all of that, and we're multiplying it by 2 yet again. And so E1 times A1 is going to be E1. G times G is G. E1 times A2, I'm going to use this little table here, it's E1. And then I have E1G times E2G, and I'm using the D6H character table, which may or may not be correct. This is not a D6H model, but it's what we have to work with. E1 times E2 is B1, B2, and E1. And so I have something of order 2 times something of order 4. I should get something of order 8. I have 2, 4, 5, 6, 7, 8. That's kind of nice. You just kind of see that order. But I don't have A1G in there, do I?
No.
And if I don't see A1G, it's not allowed. So even though there was the possibility that it would be allowed with 2 U's, with an even number of U's, using this D6H character table, we see that it would not be allowed. Now, we really don't have enough information because we don't have the real character table, but for what you have in your hands, you know, this is the way you would do the problem. Of course, am I going to ask you the infinity H question and not give you the direct product table? If I was an idiot, yeah, but I'm not going to do that, obviously. It's just the way we end up in class. Okay. But you see what you would do. You would identify the symmetries involved, and then you would go to the direct product table. You would set up your transition dipole moment, and then you would decide whether the peak was allowed or not allowed based upon the direct products of the symmetries of the molecular orbitals and the symmetry of light as it comes in and interacts with the system. Is this starting to seem easier as we go along? It should. Let yourself get it. Okay? A lot of people start out and they sort of cement their mind. It's like, oh, this is too difficult. I'll never get it. Don't do that to yourself. A lot of this is psychological. And you got to let yourself grow into the material. And you got to imagine what these wave functions are doing. Did we spend a whole hour on that one? Pretty much, 45 minutes. That's great. The ammonia is fun to do. We're not going to have time to do it in 4 minutes. I don't know, maybe we'll do it on the final review, just to kind of show. But any final question? We have 4 minutes for questions. I know people don't want to ask in class, but that's dumb. Okay. Yes?
Is the PZ orbital always going to have a sigma bonding or anti-bonding, or is it just depend on the molecule?
For a linear molecule with that z-axis, all those PZs can only interact end-on. So they're either going to be sigma or sigma star. Yeah, they cannot, since they're not off-axis, they can't bond side to side. So yeah, the PZ orbitals in a linear molecule are going to always bond end-on, which is always a sigma arrangement. And so you might think of allene, although it's not, allene is, No, let's not do that. Carbon dioxide. Okay, think of carbon dioxide. The carbon in the middle, it's got that PZ orbital. The oxygen's on either end. PZ orbital's a linear molecule. That's the Z-axis. And so those sigma bonds of the oxygens to the central carbon are end-on interactions with the p orbitals. That would be a fun MO diagram to do, right? Because you've got the carbon PZ, you've got the PZs on the oxygen, and now you could have this one be bonding and that one anti-bonding, this one be bonding and that one anti-bonding, or all of them anti-bonding. So you've got all kinds of things, arrangements. They could, all be in phase in the bonding area, and so you could have bonding, kind of anti-bonding, and really anti-bonding. Just in the sigma bonds. And then you have all the p orbitals acting side on. You have the x's making a pi bond here, while the y's are making a pi bond. You could have the x's make a pi bond while the y's are anti-bonding. And so you have all these molecular orbitals. It'd be a disaster to try to do in 15 minutes. But it would be fun to do. So if you want to have some fun, do that in your notebooks. All right, I'll see you next time.